My name is Ben Evans. I am a research consultant here at the Yale Center for Research Computing. We here primarily help to run the high-performance compute clusters, but we also help people basically get their research done in a computing environment. The way I'm going to help you do that today is to give you a brief introduction into how to use Linux from the command line and try and convince you that, especially for certain things, it's very powerful and worth using. Perfect. So everything that we do today is I sort of pre-recorded myself doing and is stored at this address here on our GitHub site. So if you wanted to go home, I'm going to give you some not graded, not turned in homework to do if you want to practice when you go home if you don't have a specific example to try and start working on immediately. I encourage that. And there's no such thing as dumb questions. If you're thinking it, probably at least one other person is, and I invite you to stop me and ask questions so that everyone understands things as well as they can. For those of you who are just arriving, especially if you have a Windows computer, you might have to download a single program in order to get set up. We're going to go over this site in just a second, but navigate to the setup page, which is a link in the top left-hand corner of the website we have set up for the course. I hope I'm not being too introductory, but I just wanted to go over computers and how we use them in research. So our computers do sort of four primary things for us. They run programs, they store data, they communicate with one another over various kinds of networks, and then the most important part for us squishy humans is that they interact with us and we can interact with them. And oftentimes nowadays this is through graphical interfaces, so windows with mice and clicking places, but there's a rich, deep history in interacting with our computers explicitly and exclusively through text. Go over ways in which to do that today, and that's typically done through what's called a shell, or a program that sits and waits for us to type a command, and then when we indicate to that program we're done with that command, it will try and do whatever we asked for it to do. And I personally learn best through example and motivated examples. So today we're going to use the example of a young, enterprising graduate student named Nell Nemo. She got back from a research trip. She has some data she needs to sort of process in a batch fashion. We're going to go over, as we learn, we're going to go over sort of how that applies to her research program and of what she's trying to do. The site itself, and I'm going to follow along with you guys as we go through these exercises. Get set up. So those of you who did register ahead of time have all been provisioned what we call virtual machines, or sort of computers that are running on other computers right now in the cloud on Amazon. And this is being done easily with a service that I'd be happy to show you how to use afterwards, called SpinUp. There's a small amount of hardware that they've been able to set aside that you can create your own small virtual machines here for free, so you can sort of test out Linux for your research without having to worry about getting a bill for it. And then if you ever wanted to scale up, you could either come talk to us about how to run those on our clusters or run it on virtual machines in the cloud with others. If you click on this down arrow right here, you should see a table of net IDs, IP addresses, and host names. So find your net ID. And then if you're on a Mac, find your terminal app, either by searching in Finder, going to your apps, and I think it's The window should look like this. And you're going to type in that window SSH, your net ID, @, and then the host name that you find in that table. And it should ask you about a special fingerprint. Just say yes. And then it'll prompt you for your net ID password, the one that you log in. And open a program called Putty. Windows users, you'll download Putty, and when you run it, you should see a window like this. And in this host name or IP address bar right here, you're going to put in the host name or IP address from that table. And then click Open. It will prompt you for your username, which is your net ID, and your password, which is your net ID password. So how many people who would like to follow along on their computer have been able to do this? Raise hands high. All right, good. How many people still need help doing this? I have 2 here. Cam, can you take a look? So those of you who have connected or who are working on your Macs, those people that walked in, you're going to want to download some sample data we're going to work on today. And the command to do that here, you can just copy and paste. And then you're going to unzip that file with the sample data. And if you're working right now, it should look something like that. So we're going to wget or webget this address. It's going to download a zip file, which is just a packed up and compressed directory. And then we're going to unzip it with the unzip command. Ta-da! All right. So, talk to you a little bit about Nell's pipeline. So Nell just got back from doing a survey. She did some field work, and she's bringing back with her some data. What she wants to do is she has a software program that she needs to run to analyze and do some statistics on each of these data files. And then she wants to be able to compare those statistics. And finally, she wants to be able to write up those results and send them to an upcoming special issue of Aquatic Goo Letters. So there's a time crunch, so she can't just do everything one by one. So she's looking for a faster way to process all of these files without her having to point and click on each one of them. So she's decided to use Linux to do so. So now that we're all in our shell, either on a VM or on your personal machine, I just want to go over a couple of conventions. First off, oftentimes if you see a $sign at the beginning of a command, either here or on other websites across the internet, you don't usually want to copy that if it's the beginning of the line. Oftentimes that just means this is the beginning of a command. And if you look at your what we call command prompt, or the text that's on the screen that you haven't typed, it oftentimes ends in a $sign. So that just means this is a command that you'll type. So don't copy and paste the $signs at the beginning of your commands. The first command I want you guys to try and run is type who am I, all one word, and then hit enter. So Nell types that. She should see that she's Nell. And you guys should probably see something with your net ID in it, maybe a longer string. So what just happened? We typed who am I, and the shell that we're using, called bash, goes out and tries to find a program called who am I, and when it does, it runs that program and displays the output that that program gave it. So going down our list of things you need to know, who, what, when, where, why, it's also oftentimes useful to know where you are in your shell. So to print the current working directory, you say, you type pwd and then hit enter. That's print working directory. So that should show you, for Nell, it's /home/Nell. For you, it might be a slightly more complicated directory on your virtual machines, or on your Macs, it would be slightly different. So that is the directory or folder that the shell is working in right now. The way that directories are specified in this sort of operating system is with slashes and file names. So if that directory that we were looking up earlier was, she was in home Nell, so the slash means that this is the root of all the files on this computer. And then there's a home directory called home, and then Nell is in yet another directory down called Nell. And the way that we're looking at it, we don't know if there are other directories in home or other directories in the root directory. All we know right now is when we type pwd, it's telling us that we're in /home/Nell. So that's what those slashes mean. It's just levels of hierarchy in those directories. To learn what files are in our directory, we can type ls for list. So when Nell types this, she sees a file called pil-data, which is that zip file that hopefully you were all able to download. And then she also sees the directory that was unzipped from that zip file. So there are very few commands or programs that you would run on your Linux workstations that don't allow you to modify their behavior. And oftentimes this is done using a flag, and what we call a flag. And for most of these, there's usually you type the command and then a space and then something that modifies the behavior of that command. In this case, we're going to type a dash or a minus sign and then a capital F. And another convention to keep in mind is oftentimes when someone says, type the command ls-f, what they mean is type the command ls and then space and then minus sign and capital F in this case. So oftentimes people leave out the space, and you just have to know that the command that you're typing is ls. So let's try typing ls-capital F and see what that shows us. So what it does for us here is it adds a trailing slash for anything that is a directory or a folder. So that's especially helpful if you're running on a machine that isn't color coding things for you, as this one is.
How do you get it to color code? Because I've been in terminal on this computer before and it hasn't color coded like this. Is there something you did?
Yes, and I can go over that afterwards. Oftentimes, there are a couple ways to get help on a command, and two of the most surefire ways are with a flag asking for that command to output some help documentation. With ls, a simple way to do that is with ls space double dash and then the word help. You should get ls to print you out a bunch of different options and how that can modify its output. And there's also a separate command that keeps a database of help files for many of the programs that are on your computer, called man, short for manual, not short for the human man. And so to get the manual listing for ls, you would type man space ls. And then you can scroll through that output, and when you're done looking at it, you would type the letter Q to quit. And I want to alert you that many of the man pages will seem like complete gibberish when you first start. And all I can tell you is it gets better, and that Google is your friend, and so are we. We hold office hours, and we respond to emails, and we're here to help. But hopefully, by the end of the day, you'll be able to understand a little bit more of that. Not only will LS take flags about how you want things to be listed, but you can also tell it to list the contents of a directory that is not the current directory by typing the name of the directory you would like to be listed. So if you type ls-F and then a space, pil-data, the name of that directory that we saw, it will actually list the contents of this, not the contents of the current working directory. So you can see there's a bunch of stuff down in our sample data directory. So it's also oftentimes convenient so that you don't have to type out long strings of characters in order to talk about directories, to change the working directory that you're in. And we do this with cd for change directory. So in order to use cd, you type cd and then a space, and then the name of the directory you'd like to travel to. And you'll notice that when you do that, there's no output. Sometimes shells will tell you that your working directory has changed, but cd does not. So after you've navigated around a little bit, go ahead and type pwd to make sure that you are where you thought you would be. And then in this example, we've gone into the pil data/data directory. So we've changed directories twice. And then in that directory, if we type ls-F, we'll see the contents of that directory, the sample data directory. So you see we have some amino acid data, an elements directory, et cetera, et cetera. If I'm ever going too fast, raise your hand, please. So, for anyone who's yes.
I have a managed workstation, so I just download and install it.
Oh.
So the command, the instructions on the website are not working.
On the website, they're not. Cam?
Yeah, but I'm trying to help them.
Are you trying to? Okay. 2 seconds.
I can hit him afterwards.
Okay, perfect. Thank you. So for those of you who have navigated around a little bit, maybe you would want to go back to the root of our sample data directory, the pil-data. So if you've navigated away from it, you might think that you could just type the name of that directory to go back to it. But what happens when you do? You can all just press play if you want to know. But what happens when you do? Anybody? Does anybody know? Yes, CD can't find it. Does anyone have an idea why? You can also scroll down for spoilers. So when we type, yes? Who said? Yes.
It only looks like down, not up. So you're already in that directory. It's only going to look for folders in that directory.
Exactly. So when I type cd and then pil-data, cd only looks in the current directory for a directory named pil-data. And if it doesn't find it, it says, I don't know what you wanted me to do. I only do exactly what you tell me to do. And then if you're lucky, you'll get an error message that hints at what you've done wrong. So there's no such file or directory in the current directory. So there are some shortcuts that have been built in for us. So say we wanted to go back to that directory just by going one level up in the hierarchy of our file system. What you can do is just type cd ... So that's a shortcut for saying the directory immediately above mine. So I type cd ... Now I'm back to the directory that I wanted to be in. Yes?
Let's say you use CD, do you have to always specify the file that you want to go into? Or let's say you just one file in that file, and you say CD and go to a file.
So if you type, I think we get to it in a second. If you type cd with nothing, it will actually take you back home if you ever get lost. cd needs to know where you want to go otherwise. So now that we're back here, I'll show you another thing about ls. So we can give it multiple flags to tell us more or less about the directory that we're in. And if you give it the -a for show me all, what it will do is it will also show you files that are hidden by default. One of these files is that special shortcut we use, the double dot. Another is a special shortcut that's just a single dot, which means the current directory. And then oftentimes there are files that are hidden by convention by default, and those files that are hidden by convention by default are prefixed with a dot. There's a lot of dot going on. So there's sort of three different ways in which the dot is used. And that's an example of each of them. So here's our example here. So if you just type cd, what happens? You just go home. You go back to your user's home directory. And so for now Nemo, that's /home/nel. So let's go back down into our data directory. I just want to get you guys some practice navigating your directories on your file system. So you type cd and then our sample data directory. You can actually do it in one command instead of two with slashes. So you can give cd an entire path instead of single directories. And I want to talk briefly. So what we've been doing so far is using what we call relative paths, or we've been talking about directories based on where we are. And another way to do this that's agnostic or doesn't matter where your current working directory is by specifying an absolute path. And these always start with a slash, meaning based on the root of this computer's file system, I want to go to root, home, nel, pill data. So this will always take me to that directory no matter where I am on the computer. So that's an absolute path. Before we were talking about relative paths being relative to the current working directory. No, an absolute path can talk about anywhere. So this is an absolute path to this directory. It's the leading slash. So home is a directory that is in the root directory, the root of the file system, and nel is a directory inside there. So that if there was, say, a bin directory for binary executables, which most systems have, it would be /bin. So that would be the absolute path to that directory.
Could you write, instead of /home, could you write cd/nel/pildata?
So if I wanted, so if I wrote cd/nel/pildata, it would only work if there was a directory in the root of the file system called nel. Otherwise, it would say I can't find that. Because the one that we're in is actually in the home directory too.
So with the absolute path, you have to start with directories that are in the root.
Correct. with the absolute path, you have to start with directories that are in the root. I'm repeating for YouTube land. I just want to go through two more shortcuts. You can specify absolute paths that involve your home directory with the tilde, the squiggle line. That is usually above the tab key on US keyboard layouts. So that you can use as a little shortcut that is an absolute path, but you don't have to type /home/no. The other thing that you can use is a dash or the minus sign. So if you say cd space dash, it will just take you to the most recently visited directory. So for many of our examples, it would just take us backwards or forwards one. But if you're switching between two directories that are very far apart, that can be useful as well. So let's look at some of Nell's data. So what she wants to do is list the files that she has. So in that sample data directory, there should be a directory called North Pacific Gyre. And then inside there, there's a dated directory. You'll notice that she's labeled it year, month, day. That's a very convenient way to name your dated directories, because when you ask a computer to sort them, they'll sort of sort by date automatically. If you're ever laying out your data in a directory, I recommend writing dates this way. That makes for everything else to be a little bit more convenient. Since this is such a task to type, she uses a special shortcut that I didn't tell you because I'm evil like middle and high school math teachers that make you do it the hard way first. You type ls and then just start typing the name of the thing you want, and then hit tab. Bash will try and finish what you were typing. I think this has saved like hundreds of years for me. So she types tab, and then it'll finish that directory name for her. And she can hit tab again, and if there's only one directory there, it will finish it for her again. So typing isn't that bad. So ignore, and then it's tab, and it completes, and tab again, and it completes. So it's a nice shortcut. Also cuts down on mistyping. So if it's tab completed, you know it exists. Okay, so I left you some homework. Feel free to do it. Feel free to ignore it. Are there any questions about this first navigating directories portion? All right. Oh, yes?
So you have to, if you want to use tab, you have to put in at least one character in the tab.
If you want to use tab, it's usually good to put in at least one character. If you hit tab twice, it'll show you everything that possibly matches, and so if there's no characters, it'll just show you everything in the current directory. All right, so far we've done nothing creative or destructive. So let's start doing that. So everyone, no matter where you are, let's make it back to the sample data directory so that we're inside our sample data directory, and let's make a new directory. So the command to do this is called mkdir, make directory. And to make a directory, you say mkdir, or mkdir space, and then the name of a new directory you'd like to create. In this case, Nell is feeling very enterprising, and she's going to start working on her thesis. So she makes a directory called thesis. And to verify that it's been made in the current directory, she types ls space -F. And so she sees a thesis directory now. Is everyone able to create a directory? You guys are going to be pros in no time. So some tips. I wish I could enforce them as law, but I can't. It's a lot easier, especially when you're using your computer from a graphical interface, to put spaces in your directories and file names. Isn't a great idea, and it can cause problems for you later on when you're doing more advanced stuff that we'll get to hopefully towards the end of this session. I recommend instead using dashes or underscores, but I can't stop you. All right, so let's navigate to our thesis directory and type ls in there, and hopefully you don't see anything. If you do, you've been hacked. Someone's on your computer with you. So oftentimes, especially when you're working on a remote computer, it's not the most convenient thing to edit a file and then transfer it there, try and do something to it, transfer it back, edit it more. There are much more powerful text editors out there, but the one I'm going to show you today is a really easy and simple way to edit a plain text file. And it's a program called Nano. And so if we wanted to create and edit a new file in our thesis directory, and maybe call it draft.txt, we would type nano and then space, and then the name of the file that we want to start writing to. And you should get an interface that pops up that looks very similar to the one we have here. So it tells you the name of the program, the name of the file, some other information about the file, and then it'll list some shortcuts down at the bottom. And when it opens, if you type letters, you can just sort of start typing text into this file. And then in order to save it, what we have to do is tell Nano to take the text that we just typed and write it to the file. And so we do this by typing control, which Nano specifies with a caret. So control and then the letter O will write out. So it'll save our changes to the empty file that we created. And then to exit, after we're done editing the file, we type control and then X. So again, after we're finished here and you go home and you frantically Google and try and find something that we've done, there are several ways in which other people and other guides specify control and then a character, and these are some of them. Nano uses this. So say we thought that draft wasn't worth keeping, which is kind of a bummer, but that's okay. We can delete the file by typing rm for remove, and then the name of the file. And then you can type ls after you've removed it to make sure that it's gone. Is everyone able to delete their draft thesis? So, unlike a lot of the graphical ways that we delete files, it's usually moved to a recycle bin somewhere, so you can recover it at some point. When you type rm and then the name of a file, all records pointing to that file are gone. So it's very difficult to recover that file when you type that command. So be careful when you use the rm command. So let's get some more Nano practice. Open up another draft. Type some more words. Save that with Control O. Exit with Control X. Save our draft. Let's go one directory up into our sample data directory so that our current working directory is pill-data. And we'll learn about deleting directories. So say you were fed up with this thesis directory and you wanted to get rid of it and everything inside it. You might think that RM might be able to do that, and it can. But if you type RM and then the name of a directory, it's going to be upset with you. This is sort of a safeguard built in so that you don't accidentally do something that you'll immediately regret. But you can override this with the -R flag to RM, which means recursive. So start here and traverse everything inside this directory and delete everything up to, but not including the directory that I'm in. I recommend, especially when you're starting out, if you do an RM-R, you also include the -I flag, which means do this interactively. So ask about each thing you're going to delete so I don't accidentally delete something great. So it'll say, okay, I'm going to go into this directory. You can type Y for yes. I'm going to delete this file. Type Y for yes. And then I'm going to finally delete this directory that is now empty. So you can also say Y for yes. Is everyone able to recursively remove their directory with their thesis in it? Awesome. So just like CD and LS, Nano, you can specify paths to things. So say we wanted to make a new directory called thesis. So let's do that again. And you wanted to edit a draft.txt file in that directory without having to change your working directory to thesis. You can type nano thesis/draft.txt, and you'll be editing that file in that directory without having to be in it. So we make the thesis directory, and we can edit yet another draft. And we can save it with Control-O, exit with Control-X. And if we do a directory listing, we shouldn't see draft.txt in our current working directory. But if we do a directory listing of thesis, you should see draft.txt. So say you wanted to move that file somewhere else. What we could do, and the simplest way, the simplest case of moving a file is actually moving it to the same directory with a different name, and this is how we rename things. So we could move the draft.txt file to a different file, for example, quotes.txt. So we type mv, the name of the thing we want to move, and then what we want it to be. So you see we've effectively renamed thesis.txt to quotes.txt. You can also move that file to different directories. And if you don't want to rename it, you don't have to say anything about what you want the file to be named. You just have to specify the directory to which you would like it to be moved. So here I'm using the shortcut for current working directory by typing mv and then the name of the thing I want to move, which is the file called quotes.txt in the directory thesis. I'm saying move that to the current directory with just a single dot. And so you see, if I list the directory that it was in, I shouldn't get anything. If I list the current directory, I should see a file called quotes.txt. So you can also make a copy of a file with another easy to remember 2-letter command called CP for copy. And it works the same way. You say copy the name of the thing I want to copy and where I want it to be copied to and what it should be named. So in this case, we're copying quotes.txt back to thesis as a new file with a slightly different name. So now I have 2 copies of this file. And what I can do is ask ls to list both the current and the directory thesis. So it'll say, in the current directory, this is what's here, including your quotes.txt. So it's still there. And then in the thesis directory, I have my new file that I made a copy with. And then just to prove to ourselves that this is a copy, we can delete quotes.txt. And if we look at directory listings, you should see that that one is gone, but the copy that you made in your thesis directory is still there. Everyone good? So, last quick note. We were calling this file quotes.txt to indicate to us that it is a text document. But especially on a Linux computer, that what we call a file extension, or the dot and then some number of letters afterwards, is more of a hint and not a hard and fast rule. So we could have moved that file to something .pdf, and that wouldn't make it into a PDF file. That's just a convention that computers use. And it's good to follow, but just so you know, you can rename a file with a different file name extension, and it won't automatically change it into that kind of file. So there's some more copies and RMs that I invite you to give a try at home. Any questions about navigating, creating, and removing files and directories? All right, so now we get into the cool stuff. So there should be a directory called molecules. We have some PDB files in this directory. Does everyone see molecules directory? Trying to crush this. So Bash gives us some fun wildcards we can use. It's called file globbing. And the first one I want to talk to you about is the star, which just means any occurrence of 0 or more characters. So basically saying anything can be here. I just want it to end, in this case, in .pdb. And we're going to use the WC command for word count. So I want to know how many words there are in each of the .pdb files. So instead of typing out this command and then cubane and then this command and ethane and this command and methane, what I can do is say WC, show me the results for each of the files that satisfy this wildcard that I've specified. And WC by default, I believe, gives you lines, word counts, and character counts as 3 columns. And then a total at the bottom of everything that it's counted for you. So if we just wanted to know how many lines are in each file, we can give WC a flag, the -L for lines. And then it will show us just the number of lines and the file name for each of the files, including a total. So you can start to imagine how this is beginning to be useful to us. If I were on a Windows or Mac and I want to know how many lines are in each of these files, I'd probably have to open them by hand, each one of them, and somehow calculate the number of lines and then close them. So if you wanted the number of words, you would do a -W, and the number of characters, you would do -C. The other really powerful thing you can do with this output is redirect it. So the first way we're going to redirect it is into a file. Yes?
So I'm hoping when I do the help function, when I do help on the word count, it said that -C is printing out the byte counts.
Right. So for an ASCII file, byte counts is going to be close to character counts, probably. Is there a character count option?
Yes, so it's
-M. Okay. So in this version of WC, -M would give you the real character count. Yeah, we're not going to do it. So we're concerned with lines for now. So we're going to stick with WC-L, which your WC does do lines with WC-L, right? You saw the same output. So say we wanted to save the output from that command so we could use it later for something. We can redirect that output into a file with the greater than symbol. Think of it more as an arrow, which direction it's pointing. So I can say WC-L, start at PDB, so all the PDB files in the current directory, and save that to a file called lengths.txt. And to see the contents of that file, we can type the command cat for concatenate. If I type cat and then the name of a file, it'll just print everything out from that file to the screen. So in this case, it should be the exact same output that you saw when just running this command, but now we have that output saved in this file here, lengths.txt. So another more powerful text viewer that I like to use and I use every day is called less. So if you type less and then lengths.txt, it'll show you that file. And if it's longer than a whole page, you can sort of navigate around in that text file without having to scroll up and down in your terminal viewer. But we can get to that more in depth later. Another useful command I'd like to show you is one called sort. So if I do sort and then -n for sort this output numerically, and then lengths.txt, what it'll do is it'll sort each of the lines in that file based on these numbers that appear here. So you'll see the shortest file is methane and the longest file is octane. So again, we can take the output from our lengths.txt and redirect it to a new file called sortedlengths.txt by redirecting it with this greater than symbol as an arrow pointing to this is the output I want it to be. And say we only wanted to see a small portion of a file. We can use the command head for just show me the head of that file. And then with option -n, we can say the number of lines that we would like to see. So if I said head -n1, it'll show me the very first line of that file. So the very first line of our head -n1 sortedlengths.txt will be the shortest length file. So something I didn't tell you is when you redirect output to a file, the first thing that happens is if there is a file of that name, it gets blown away. So make sure you either didn't care about that file or it doesn't exist yet when you're redirecting. So there's another way we can redirect output, and that's with what's called the pipe character. It is oftentimes over the enter key on US keyboards. And what it tells us, and what it tells Bash to do is take the output from this command and use it as input for the next command. So we can start developing a pipe line. So without creating that, what did we call it? Sorted links.txt. Without even creating that file, we can say sort this file and then use that output as input for head. And head will only show you the first line of that output. So you can say, I want to know what's the shortest thing from links.txt. I can do this without having to create a file to do it. So we can also walk backwards and recreate our sorted links.txt file without having to create our links.txt file. So we can use our wc-l command and pipe that. So use the output from this command as input to the sort command. So then our output is the sorted links of these files. And finally, we can get a result without having to make any intermediate result or any intermediate files at all by piping all three commands together. So start out, what are the links of all of the files? Sort them for me, and then only show me the first line. So that you definitely can't do easily by pointing and clicking. So here, I just have a graphic that helps me understand sometimes where when we type our first command, it's actually just outputting to the shell, which prints it to the screen. And when I ask it to redirect, it's going to this file. And then when I'm piping it, it's actually being used as input between. So the output from WC gets used as input for sort. Sort then outputs our sorted output from here, and that's used as input for our next command, which is head, which then I'm telling it, just give me one line. And then finally, since I didn't redirect that to a file, it'll print out to the screen. So you can sort of filter out results that you don't care about with pipes, and then you can redirect those either to the screen or to a file if you'd like to save them. So, now that we know a little bit about how to parse through files and sort of filter the results of that, let's dig in a little bit to Nell's data. So, if we change directories to her data directory, you'll see that she has a bunch of sample data. And if the data is formatted properly, it should be exactly 300 lines long. So you'll notice that not all of them are. This is a good way for her to sort of spot check her data. And then if she notices that there are certain data files that aren't the right size, maybe she'd want to sort based on the number of lines, and maybe just look at the first 5 to see how many there are, so it all fits in one screen. So since this is sorted, we know that everything below here is 300 or greater. So there's really only one that's too short. So that's good, probably. And then we can use a command that's sort of the opposite of head. It's called tail. So it just shows you the bottom end lines of your input. So we know that now none of the files are too long either. They're all the rest of them are 300 lines long. So the only last surprise that she has is the way that she's named all of her data. It's supposed to have an A or a B. And one of the students that she brought along with her maybe named it with a Z there in the file type. So what she can do is list all of the files that have that Z in that place with a wildcard by typing ls star z.txt. So she can tell that there are two. That's a nice application of wildcards there. So those files she probably would want to exclude from future analyses. Another way that she could talk about just files with A or B.txt, I write out in the very bottom of this page here. So if you put characters in between square brackets, Bash will look for anything that has either this character or that character.txt. So this is a single character that is anything in between the two square brackets. More homework. Any questions about pipes, redirection, filtering things? No, we're all pipeline pros now. All right. So I want to talk about loops, specifically for loops. We're going to do a little bit of programming today. I'm going to start with an example. So say I wanted to copy all of the files that satisfy some specification. So here I want to copy all of the .dat files, and I wanted to make a backup of them so that I'm keeping my original data separate just in case it gets modified and I need to go back to the beginning of my experiment. You would hope that you could type this, cp star.dat, and then just have it rename every file as original dash that thing. But cp doesn't work that way, because what actually happens behind the scenes is when bash sees the star, it actually fills this in for you. So you say cp star.dat, and it'll actually say, what cp ends up seeing is cp every single dat file that's in our current directory, and then this thing that we typed, bash couldn't find anything that satisfied that, so it just says I give up. Maybe you're talking about a real star, and we get this. So this is what cp actually sees, which you can go ahead and give a try or click play. So if you give cp a list of files, it expects the last thing to be a directory to move all those files to, because that's the way whoever designed cp wanted it to be. And when that's not a directory to move all those files to, it says, I don't know what you wanted me to do. You didn't do what I expected. So it throws its hands up and gives up. So probably the easiest way to take care of what we actually want to do is with a for loop. And a for loop, like its name says, for each of the things I want to work on, do something. And the syntax for it is you type for, and then a variable name that you want to be able to refer to each thing as, in, and then a list. And in Bash, you can space separate lists. Can you see why you might not want to put space in your file and directory names? So I say for a file name in this list of 2 files, I want to do something. I would type do. And then a simple thing to do would just be to look at the first 3 lines of that file. So I would type head-in 3 for the first 3 lines. And then when I refer to that variable inside my loop, I use the $sign and then the name of the variable to tell Bash I'm referring to the variable. And then when I'm finished with my loop, I type done. And what Bash will do is it will say, so for each of these, so it'll loop twice because I have 2 things in my list. So the first time it'll go through and it'll say for when file name equals basilisk, head-in 3 basilisk. And then it'll do it again for the next thing, head-in 3 unicorn. So you can type out a for loop in your shell. And you can tell that Bash is expecting more when it gives you these greater than symbols, not to be confused with file redirection. I didn't make the rules, I just have to follow them. So what I did is I get 6 lines, the first 3 from basilisk and the first 3 from unicorn. You can. Here's an example right here. But before we get to that, I just want to talk about variable names. Don't be afraid to, especially computer scientists are guilty of this because they're used to trying to be as terse as possible. So sometimes you'll see for loops where it's X or Y or I. And especially if I go back and look at my code from 3 months ago, I don't remember what X means. Also, this is less common, but don't use words that don't mean anything in this context. So I don't know what temperature means either. Try and use words that are descriptive to you and the person sitting next to you. This may be familiar with your work, but wouldn't know what your brain looked like on that day. So I'm going through a list of files, so I'd call them each a file name. So that's what we're going to use as our variable name here. And then like you said, instead of typing out those files, you can use a wildcard, and then Bash will expand that to what we were typing before. So the for loop sees the same thing, but you don't have to type out all of the .dat files. Inside our for loop, we can have more than one command. Oftentimes when I'm constructing a for loop, one of the first things I do is have Bash tell me what the variable is each time the for loop iterates or goes through one thing in the list. And the way that you can ask the simplest way you can ask what a variable is by typing the command echo, and then space $sign the variable. And what we'll do is we'll just echo out the contents of this variable to the screen. And then, we could ask for the last 2 lines of the first 100 lines, so some middle part of this stat file. If we wanted to just see that file and some sample of its innards. So we can sort of get a flavor for all of our files in this directory with this for loop. So for variable name in list of things, do the following. Here's some commands that I want you to run. Here's our pipe redirection. And then when you're done with the for loop, type done. And you'll get here, we're echoing out file name, the first file name, and then getting the first 100 lines and then the last 2 of that, and then the same for the second file. So those kind of look like DNA sequences to me. So again, please don't put spaces in your file names, because then you can't do fun things like this without being extra careful. So here I have a more diagrammatic version of what we're doing here. Each part of our loop will start out, ask if there's a new variable that's available. So is there more in our list? And if that's true, it'll run what we asked. So in that last example, it's the echo and the head and tail command. And then when it's finally finished, it'll stop, and then the command prompt will be waiting for us again. So, did I skip one? I guess I don't have a play for this. So to go back to our original problem where we wanted to copy a file, a set of files into original dash that file name, this is the for loop that we would actually want to do. We would want to, for each file name, copy file name and then original dash file name. And what copy we'll see is, unicorn, original dash unicorn, et cetera, et cetera. This is a simple way we can sort of back up all of our data in the same directory so that we don't accidentally edit it in some way that then we can't go back to our original data and double check. So for now, she wants to be doing things to, if you recall, just the A and B ending files. So her for loop is going to look something like for data file in star square bracket AB other square bracket .txt. It's going to say for each of these files that is satisfied by this file glob, do the following. And oftentimes when you're starting to construct a loop, it's nice just to see what your variables are evaluated to. So she just starts out saying, basically rewriting ls. This is what ls does. It just lists the file names. She's just saying, show me the value of every variable in this loop. There you go. Not very interesting. So say she wanted to maybe have a results file that's called stats and then dash the name of the data file. So she knows that these new files will be something about statistics on that data file. But she doesn't want to create them yet because she's not sure yet exactly maybe how this looping works or whether or not this will work how she expects it to. We can again use echo to check what our variables are being evaluated to. So now you see a list of the original files and how she wants the output files to be named, which is helpful when you're constructing your for loops. Again, a shortcut that I didn't tell you about yet, but is very useful. The up and down arrows you can use to recall commands you've typed before. And when you recall a for loop, Bash will put in semicolons where there would have been new lines in the for loops that we were doing before. So if you hit the up arrow, you should see the entire for loop on one line with semicolons. And there's nothing wrong with running that same command and editing it. So Nell is sure that her file names and output file names are right. What she can do is have it run the statistics program that her advisor gave her, called GooStats. And GooStats accepts the name of the file and the name of the output file as arguments. So what she can do is she can make this this loop do all of her work for her. So do all of my statistics on every single file, and when you're done, you'll be done. However, she also wants it to tell her its progress, so she puts back in an echo so that she knows what file is being worked on. So now you can see it chewing through each one of the files, and she doesn't have to sit and watch it. She can go get coffee. She can go check Facebook. And last but not least, sort of the quickest and dirtiest way to remember what you've done is by using the command called history. So I think by default, usually it's about 500 lines of what you've typed, Bash remembers for you. And if you wanted to save a particularly useful command, the fastest way to do so would be to save your history by redirecting history to a file. And then with some light editing, you could almost create a script with that. So, loops, questions? Yes?
Can you say what echo does?
Echo echoes whatever input you give it. So you could actually say echo and then string. You could say echo me, and the next line would be me. And the useful thing about echo is it will show you interpreted versions of variables. So if you say echo $, one of the variables, it won't tell you the exact text you typed, but what the contents of that bash variable. So so in this example here, I'm typing echo this variable, and then a space, and then these letters, and another variable. And what echo gives me as output is the contents of data file, the variable, the letters stats dash, and then the contents of data file again here. You can use it to construct new strings around existing variables. And echo is a great way to check to make sure that you're doing what you think you're doing before you actually execute a command. Cool. All right. So we've been doing a lot of useful things today. Let's say you wanted to go back and reuse commands that you've run in the past. Bash affords us this in what are called shell scripts. So we can save commands and then parameterize them or make them more useful in different situations. And I'm going to show you how to do that now. So let's go back to our PDB files, so our molecules directory. And let's make our first bash script by opening nano with, what was the script called that I made? Let's call it middle.sh. So again, say we wanted just a sample of a file by looking at the first 15 lines and then the last 5 of those. So I could type this on the command line and it would give me some output. But let's type this into a file and save that file. Control O to save, Control X to quit. So now you should have a file called middle.sh. And bash is really cool. If we call bash the program and then give it a file, it'll try and run every line in that file as if you typed it. So when we type middle.sh, it'll run the command that we saved in that file. So it'll give us these 5 lines from the middle of that file that we typed up here, which was Octane. And if you want to, you can copy and paste that command into the interactive command line. You should see the exact same results. So instead of, that seems kind of silly though, right? Because it's just one file and we can type that command. But saving it as a bash script, we can change it, and instead of having a static file or file name, we can begin to make it more useful by talking about the words that come after the script when we call it. So open up that file and replace the octane.pdb with a $1. And you can put quotes around it too. That can sometimes alleviate your space and file name woes, but this should work too. So when bash sees a $1 in our bash script, what it'll do is it'll look and see if we typed anything after we called our bash script, and it'll replace $1 with that. So we can sort of save the command, but then be able to replace specific portions of it with the arguments that we pass to that script. So $1 is the first argument that we gave our script, which again is the same octane.pdb. So it should be the same results, but now it's starting to become more useful because we can run this command without having to type it all out, just by calling a specific file name. So go ahead and give that a try with a different .pdb file, and you should see different output. So again, this is a little bit of a toy example, but we can talk about more than one argument given to a bash script. So go back in and replace the numbers with 2 for the number we're passing to head and 3 for the number we're passing to tail. Now, our script actually looks a little bit nonsensical, right? It's just a bunch of numbers. But what bash will do is it'll look and see the first 3 things that we type after calling our script, and it'll insert those into those variables for us. So now we can control, even though we put the same numbers here, sort of to verify that it's the exact same output, we can control the parameters that we're giving to head and tail now with these 2 numbers without having to type out head and tail. So now we can change these pretty easily while still saving the command that we were originally running. Say we did this with pentane, and then we ask for the last 5 lines of the first 20 lines. Would be this command here. So this is always the last thing that anyone ever does, but it's still almost as important as the work itself, is documenting what the heck your script does. So bash scripts, anything after the pound sign or hashtag or whatever you want to call it, bash ignores. So you can write yourself notes about what this is and how to use it. And I highly strongly recommend you do this because, again, your 3 months from now brain will probably not remember exactly what $1, $2, and $3 is. So it's excellent practice to write yourself and whoever else ends up using your scripts, little notes. So one last argument variable that I think is very useful for us to know is what if we wanted to run our command instead of one file at a time, if we wanted to run it on a bunch of files with wildcards. What we can do is use a special variable name in bash called $@. And again, I didn't make the rules, I just follow them. So you just get to remember this. But now what happens is when we run this bash script, everything we type after calling the bash script goes here, no matter how many things it is, almost. Pretty much everything. If it gets super long, sometimes you can get errors, but we can use this to bottle up commands that we want to run on batches of files. So we can give it a wildcard. We can also give it other directories. We can make this list almost as long as we want. And it'll do our old wc-l and sort-n. So it'll give us the line counts of all the PDB files. In addition to that, it'll give us the line counts of all of our creatures.dat files. And it'll list that here for us in one awesome summary.
Variables that you call as arguments after you run this script. So like what if I wanted like to do what you did before we did head in a certain number of lines
Mm-hmm.
on multiple files? Can you use $@@sign and $1 or whatever?
There's a way to talk about the rest, and I don't do bash scripts enough to remember. But
Okay.
the short answer is yes, and we'll look it up in a minute. Little gotcha here. Oftentimes, you might forget to put a variable name or an argument to one of the commands that you write in your bash script. And if you do that, what a lot of these programs will do is actually wait for input from what's called standard in, or in this case, you typing. So it'll sit without a command prompt and just wait for you to type something. And it can be kind of a weird experience at first. So if that ever happens to you, what you can do is pass the kill this process or the end of file character with Control-C or Control-D. So if a bash script starts acting up, just Control-C will usually kill it for you. And again, if we want to save our history, we can pipe our history into a .sh file. And we could almost use this as a script in itself. We just need to get rid of these line numbers here. So you could open that up with nano and Just delete those numbers. And then this you could use as a script if you wanted. So in Nell's example, her advisor came to her and said, "You dummy, you forgot to specify to goostats that you wanted the -J100 parameter, because everyone now uses that, because that's the way that we do science now." And so what she has to do, she has to go back and redo all of her statistics. And if she had done this by hand, that would be an awful task. But since we remember in our bash history the for loop that she had, we can put this into a script. And now she can pass in with the $@ her list of files that she wants statistics done on, and call her goostats script with the proper parameters. And she's all set. And there's a little bit of less. I'm going to skip through that so that we can have some time to do the last thing and have some questions. But more questions? Yes?
I have a question. So when we wrote our script, we put double quotation marks around our variable. Why do we do that?
It's not necessary unless you might have one of the cases in which it would help is if you thought you might have spaces in your file names. Sort of tell bash after there has been that variable expanded into what it says. It might save you from the space being interpreted as two separate things. But it's not necessary.
I remember sometimes you use like single quotation in like Linux system, but in general, what's the difference between single quotation and double quotation?
I believe there are cases where one or the other will force variables to not be immediately interpreted. But usually there isn't very much of a difference. That's the difference between single and double quotations for the video. Any other questions? We're going to move on to a couple of commands that, again, I use almost daily and I think you guys would find very useful. And it's all around trying to find things both inside files and files on your computer. And the first one is called Grep. And we use it to find things inside of files. And so let's go in our sample data to the writing directory, where we have some sample poems. And let's look at our haiku by typing cat and then the name of the file, which will just print it out to the screen for us. You see we have some words here in our file. And we can use grep to find lines in that file that contain a string. And so here let's look for every line that has the word not in it by typing grep and then not and then the name of the file we want to search. So you see it finds 3 lines with the characters NOT in them. Oh, that was a mess. So you can do this with a different pattern. You can find all the lines that have day in them. And you'll notice that it doesn't necessarily mean to match an entire word. So it matches today and yesterday. So grep isn't quite thinking like a human would. So if you want it to match just that word, meaning there's white space between it and other things in your file, you would use the -W flag for match words that are this pattern. So you see we didn't have any matches for day. And if we want to use a space in our pattern, we put quotes around it. So then we can find the words is not with grep. Especially if you're more interested in just summary, you can use the -N for line numbers as well. So you know that yesterday it worked is line number 9 in the file that it matched. And so you can combine a lot of these flags. So you can say, give me the line numbers where it's just the word the. And so it's just 6 and 2 in this case. Another useful flag is the -I for case insensitive. So it also match the with a capital T. Another really cool option is the -V, which means everything that doesn't match the following pattern. So these are all the lines without lowercase the. I think it's a V, an homage to set theory V. Grep has a dizzying number of options. So you can either look at the man page, you can ask for its --help, you can search Google for more crazy complicated ways of using grep. Here we're just looking at it with less. So you can scroll through all of the different options that it has. And when you're done with less, you would hit Q to be finished. Another really fun command that we are going to take a look at is called find. So grep helps you to find inside files, and find helps you to find files on your computer. The simplest thing we can do with find is just find and then a dot, which means find all the files in the current directory. So we can do ls yet another way. But it also tells us about all the files and subdirectories therein. So we can pass options to find about the file type. So say we only wanted to look at directories in the current directory. So you'd say -type and then D for directories. Go. These are all the directories. Conversely, we can look at all the things that are files. These are all files, they're not directories. So we can also use wildcards with find, but we have to be a little bit careful because sometimes bash tries to be too helpful. So if we type this, we would expect to find all the files in this directory and below that end in .txt. But what happens is bash goes through before find actually gets run and replaces star.txt with all files in the current directory that satisfy this file glob. So what we end up saying is find me a file with the name haiku.txt that is in this current directory or below. And it does. It finds that single file. So what we want to do in order for find to find these things is to surround this with quotes so that bash ignores it. So now it'll find .txt files down in our data directory. So one of the ways that we can use output from find is by using what's called a subshell. So we're saying, bash, run this first, and then use that output here. So we can combine that with our wc-l command to get line lists for all the .txt files in this and subdirectories. Yes?
We just use pi, like a pi to generate, so we say pi name txt and then slash.
Sometimes. Occasionally, find will output extra characters that are better handled this way. There's also just more of an example of another way to skin the proverbial cat. So we can also string this subshelling with grep. So we can look for iron in all the files that are named star.pdb. You see our heme.pdb lists iron. So one caveat with these utilities here is that they don't work well on files that aren't text. Oftentimes, hopefully, if you are working with binary files, you'll have utilities to search through them. And that's about it. About 10 minutes for questions. Yes?
Can you explain once again the difference between one doc and two docs?
So the difference between 1 dot and 2 dot. 1 dot is the shortcut for current working directory, and 2 dots is the shortcut for the directory above the current working directory. Yes?
When we write a script, can we do like can we modify the behavior of the script, just like when we use ls and how we have like the dash and then specify how we want to modify it? Can we do that with a script that we write?
Yes. So you could use your script to check for flags like you do ls. You would have to, in your script, write some, probably the simplest way would be able to write some if statements to say if this flag is in the parameters passed in, then modify this behavior. If you start to feel like you're making a really fancy bash script, it's almost always a good idea to start writing it in maybe a different scripting language. I recommend Python because I like Python, and we have a couple Python classes here that we give, and there's countless ones online. But Bash is really good at doing high-level stuff, sort of the kinds of manipulations we looked at here. But if you start to try and get really fancy, Bash starts to feel kind of clunky because it's not as great at doing the finer manipulations, or if you actually want to do math, for instance, it's cumbersome to do in Bash. Cool. Well, thank you very much, everyone, for coming.